Hi everybody, in lesson 5 here, we're going to work with this big concept called a sampling distribution, so let's get right to it here. So Mr. Hines was bored in an airport and flipped a coin 100 times, and it landed heads up 64 times. As he loves statistical questions, he asks himself, is this a fair coin? He needs your help to determine if the coin is fair or not. So this goes back to that idea of statistical inference that we're going to look at, where we have this population, which I guess in this case would be all my coin flips. And I want to know a parameter. In this case, I want to know a population proportion. What's the true percentage? What's the true proportions of heads? Well, I can never know that. So what I do is I take a sample. I'm going to take a sample. In this case, I did 100 coin flips. I did 100 coin flips. That's my sample. And from that sample, I can compute a statistic, a sample statistic. I can compute a sample proportion. I'm going to compute a p hat, and I'm going to use that p hat to make a judgment about the parameter. So this is kind of the idea of what's going on when we're doing statistical inference, is from our population, we're going to take a sample. We're going to calculate a sample proportion or a sample mean in some cases, and we're going to use that statistic to make a guess about this unknown parameter. Because we never know what these parameters are, our job is to figure out what they are to make our best guess at what they can be. So how many heads would we expect from flipping a fair coin 100 times? Well, if it's a fair coin, that means there's a 50-50 chance of getting a heads or a tails, so we would expect 50. Out of 100 times, I would expect 50. But what's my sample proportion? I didn't get 50 heads. What's my p hat here? My sample proportion is 64 out of 100. How many successes I had out of the total number of trials is 0.64, which is clearly bigger than 50%. 64% is clearly bigger than 64%. The question is, how extreme? Could that happen from sampling variability? Sometimes when we take a sample and find a statistic, there's this thing called sampling variability, where you don't always perfectly get 50-50 heads, even if that is the true parameter. When you take a sample, there's some kind of variability that happens with your data, where sometimes you get a little bit above, a little bit below. But our question is this 64% so extreme that we can make a comment about this parameter here? Or is it so extreme that I can make a comment about the parameter, or am I going to say, you know what, I don't have evidence. It was just sampling variability. It just happened by chance that I got 64%. So the way that we do this is we're going to use some kind of simulation to get us started. So if we were in class right now, we would all be flipping coins and having a blast, but we're not. So what we're going to do is I'm going to simulate this for you. So the way I'm going to do this is I'm going to have my computer pick me a random number, 1 or 0. Let's let 0 be tails, and we'll let 1 be heads. So right now I flipped a tails. I flipped another tails. Oh, I flipped a heads. I flipped a tails. I flipped a tails. And I'm going to do this 10 times for now. I'm going to do this 10 times for now because doing 100 coin flips would just take too much time if we were doing this in class. So there we go. I just flipped my coin 10 times randomly. I've got 1, 2, 3, 4 heads. I got 4 heads and 6 tails. But to make our lives easier, I'm going to have the calculator, and again, you don't need to know how to do this. I'm going to have the calculator add it up for you, add all those numbers up. So I got 4 heads, 3 heads, 5 heads, 8 heads, 8 heads, 2 heads, 6 heads. So what I'm going to do here, and if we were in a class, is we'd all be finding a bunch of p hats. We're going to find right now, we're going to generate a whole bunch of sample proportions, where we're not looking all at one coin flip, we're all looking at how our sample proportions that we all got. So there I had a sample proportion of 0.50, 0.2, 0.5, 0.7. And what we're going to do is we're going to generate this a ton of times. I'm going to go to a different program for this right now, actually. So here we go. Here's a different program that I'm going to do. I'm going to do one set of 10 coin flips. That's what this one dot is here. That 0.6 there says I had 6 heads out of 10. I'm going to do another 10 flips. I got 0.7, 0.5. What I'm doing is I'm doing a bunch of coin flips right now. Every time I click the mouse, I'm plotting here a sample proportion. Every time I click, I'm adding a new p hat to the board. And if we were doing this in class, this is what would be happening on the board. We would all be graphing our sample proportions from flipping our coins 10 times. How many heads did we get out of when we did it 10 times? And the beautiful thing with technology is I can quickly do 10 of them. I can just quickly generate a ton of these sample proportions. I just generated 1,000 of them right there, which is why it lagged a little bit. So notice every dot here, there's a whole bunch of dots. Every dot here represents a sample proportion. It represents me flipping the coin 10 times and determining what percent of them were heads. So notice, what is this distribution centered about? What is the shape of, this is called a simulated sampling distribution. This is a sampling distribution because it's a whole bunch of sample statistics. It's a whole bunch of p hats that I created. So what is it centered about? Well, it's centered about 50%. Why? Because what did I assume about my data? I assumed the true proportion was 50%. So it's centered about 50%. Why? Because we assume that to be the case. We assume that the true proportion was 50%. What shape is this? Well, of course, it happens to be that nice normal curve shape. It appears to be approximately symmetric. It appears to be approximately normal. And what's the standard deviation of this distribution? Well, I've calculated it for us. Oh, wrong app. I've calculated it for us. It says it right here. The standard deviation is 0.160. So the standard deviation there is 0.160. So that's just a measure of spread. So that's what we would have done in class with our 10 coin flips. We would have done that together. But that was just to get us used to the idea. Now let's go answer my question. I was actually flipping it 100 times. So let's do this again. Let's use technology to that's going to take way too long to do in person. So I'm going to change my sample size here to 100. I'm going to flip 100 coins at once. So when I click generate, this one dot right here that I just made was 37 heads out of 100. And I can do that. That's another 100 coin flips. This dot right here that I just got on here is 54 heads out of 100. And that's from sampling variability. Yeah, I assume the coin is fair, but it doesn't always mean I'm going to get 50% heads. There's some sampling variability occurring, which is why all these p hats aren't the same. So I'm going to do this like 100 times, another 100. I'm doing a ton of coin flips right now. So I'm generating this sampling distribution of 100 coin flips. I'm going to do it 1,000 times and call it a day right there. There we go. I did it 1,000 times. So what do we notice about this distribution? This distribution also has that normal curve symmetric shape. So it appears that when we make these sampling distributions, we're getting approximately symmetric shapes. What's the center of this distribution? What is it centered around? Well, the center of it is 50%, 0.5 again. Why did we get 0.5? Because that's what we assumed the coin was. I assumed I was flipping a fair coin. What is the standard error? What's the standard deviation of this sampling distribution? Remember, this distribution is a bunch of p hats. Well, it appears to be 0.05. From my calculation there, it appears to be 0.05. So what happened as we increase the sample size from 10 to 100? What happened to the shape, center, and spread? Well, the shape, they're both normal. They're both normal distributions. The shape didn't change. Both normal. The center, both were at 50%, 0.50, because that's what we assumed the true population proportion to be. We made an assumption about that parameter. What did change was the spread, the standard deviation. Look what happened to our distribution here. Here's the 100 coin flips. Let me go back to the 10 coin flips. Let me go back to the 10 coin flips. Let me generate it. Look how far spread out it is. It goes from 0.1 to 0.9. Whereas if I flip it 100 times, my spread decreases. The highest one I've got here, let me do it another 1,000 times, just for good luck. One more time. So it's spread from a low here of 33 all the way to a high here of 66%. So the spread decreased, which makes sense. It's easier to get 2 out of 10 than 20 out of 100 heads. It's much easier to get 2 out of 10 than 20 out of 100. Even though they're the same p hat, you've got more variability in your p hats when you have a smaller sample size. So the spread decreases as sample size increases. So let's answer the question now. Was my sample proportion of 0.64, what's the chance of me getting a p hat of 0.64? What is the probability of me getting a p hat bigger than or equal to 0.64? So let's use technology here to figure this out for us. So I want to know what's the probability that I get a p hat of 0.64, and I'm going to have this little applet here. Again, you don't need to know how to use this. What's the probability I got 0.64 or higher? That happened 0.0030. So that has a probability of 0.0030, or 0.3% of the time. So what does this mean? Assuming Heinz flipped a fair coin 100 times, assuming Heinz flipped a fair coin 100 times, there is a 0.3% chance of getting a p hat of 0.64 or higher. This is super unusual. Super duper unusual. That's completely unlikely to happen. This is so extreme. Something happening 0.3% of the time. So what this gives us is we have evidence the coin is not fair. We have evidence now. We have statistical evidence. We have statistical evidence the coin is not fair. And next week, we're going to look at, well, what is the true proportion of heads that this coin lands? That's what we're going to look at next week. Right now, we're just going to say, you know what? That's really extreme. We have evidence that this coin is not fair. We assumed it was a fair coin. We found the probability of getting a sample proportion of 0.64 or higher, because that's what I got, and it happened 0.3% of the time. So that's super unusual. So we're going to say that we have evidence that this coin's not fair. It could have happened. It could happen from a fair coin, but something that happens 0.3% of the time is not likely at all. That I'm going to say I'm not going to bet money on that. That's a very unlikely outcome. So that was for a sample proportion. Let's see what happens when we play around with sample means. So again, just watch. This is a lot of watching in this video and not a lot of taking notes. So here's the parent population. It's got a mean of 16 and a standard deviation of 5. And sample means work the same way. I'm going to take a sample, I don't know, let's say of 10 people. I'm going to sample 10 people from this parent population, and then I'm going to find the mean. This blue dot here is a sample mean. That's an X bar. Then I'm going to sample another 10 people from that population. Then I found another X bar, and I'm going to do that again. This is called a sampling distribution, this blue one that I'm building down here, because every dot is an X bar. In the other one, every dot was a p hat, but here I'm looking at a distribution of all the sample means. That's what the sampling distribution is. It's the combination, it's the distribution of every possible sample of size 10 in my case, because that's what I'm doing. I'm sampling 10 people at once and finding a sample mean. I'm finding 10 people at once and finding a sample mean. And I can do this, luckily, 5 times. So I'm going to do it a whole bunch of times at once is what's nice about this applet. And what do you notice about the shape of this distribution? So far, I've taken 500 samples. Let me do 2 quick ones there, just to get it to a nice number. So far, I've done this 350 times. I've taken a sample, find a sample mean. If I keep doing this, look at the shape of this distribution. The shape of this distribution is still normal. Look at the mean, 15.99. The mean didn't change. The mean of my sampling distribution is still the original mean. But what happened to my standard deviation? Which one is more spread out? Well, this has a standard deviation of 1.63. My standard deviation of my sample means, of my sampling distribution, this blue one here, got smaller. And what happens if I sample 25? That standard deviation got even smaller. So again, if I have a small sample size, my sampling distribution is going to be more spread out. But as my sample size gets bigger, my standard deviation decreases. It follows, sample means follow the same exact steps that sample proportions did. It's normally distributed. It has the same center. The average is still the same. The center of that distribution is still the original center of the parent population, but the standard deviation is smaller. So this is the key magical theorem of statistics that you don't really need to worry about unless you're taking AP Stats next year. It's called the central limit theorem, and it tells us three things. So regardless of the population, the distribution of a sample mean or sample proportion, that's our sampling distribution. When I find a whole bunch of sample means or a whole bunch of p hats, it's normally distributed, it's centered at the population mean, and the standard deviation of the sampling distribution decreases as I increase my sample size. As I increase my sample size, it's harder for my sample statistic to be more extreme. So in statistics, a lot of the times, we want our sample sizes to be large to decrease that sampling variability. It decreases the variability in our data. So when we work with a distribution of sample means, the sampling distribution of X bars, it's normally distributed. This is key here. It's normally distributed, centered. The mean of my sampling distribution is the original mean. The mean of my sampling distribution is the original mean. The center doesn't change. The center is the same. But the standard deviation of the sampling distribution, the standard deviation, we use this Greek letter sigma here. We use this Greek letter sigma. The standard deviation of my sampling distribution is my original standard deviation divided by the square root of my sample size. So, for example, I'll show you this. What's the original standard deviation here? 5. When my sample size was 25, what did my standard deviation become? Well, in theory, according to central limit theorem, it would be 5 over the square root of 25. Why? Because that was my sample size, which equals 1, which, look at the applet here, the standard deviation is 1. So this is key here, and we're going to be using this all next lesson. The standard deviation of my sampling distribution is this original standard deviation divided by the square root of n. And the same thing goes for when I work with p hats. It's normally distributed. It follows the normal model. The center of my distribution is the true proportion that we believe it to be. So the center of my sampling distribution is the true population parameter. And the standard deviation of my sample proportion, this guy's fun. It's my population proportion times 1 minus the population proportion over n. We're going to look at this in the next lesson. But in the next lesson, we're going to play around with these two formulas. So the two things I need you to leave with here today. If we're working with X bars, my standard deviation is the original standard deviation over the square root of n. If you're working with p hats, your standard deviation is the square root of the proportion, 1 minus the proportion over n. So we're going to play around with this in the next lesson, but I need you to understand this idea of sampling. I have a population. I'm going to take a sample from it. I'm going to take a sample of whatever size and find an average, and we're going to keep track of all those averages. And in theory, the central limit theorem, in theory, we know about this sampling distribution. We know it's normal. We know the mean, and then we can also compute the new standard deviation of that sampling distribution. And that's what we're going to do in the next video. So I'll leave you at that point. I talked a lot in this video. The next video will be doing lots of problems. So I'll see you there.